Hi, today's lab is Lab 13 on heat dissipation. This is Physics 241 lab. Heat dissipation is sometimes called the Newton's law of cooling. And it has a general principle. The principle is the greater the temperature differential with air, the faster the cooling rate. Now, for example, if we had a liquid at 200 degrees and we allowed it to cool in 15 minutes, and it cooled to 100 degrees, we would have a cooling rate of 6.66 degrees Fahrenheit per minute. The temperature differential here is 100. If we had a temperature differential of 50, from 150 to 100, and it took 10 minutes to cool, the cooling rate would be 5 degrees Fahrenheit per minute. So, because we have a larger delta T, a larger temperature differential, the cooling rate is going to be faster. And that's the principle behind this lab. Now we're going to apply it to an example in making coffee. Now, in this example, you brew yourself a cup of coffee, and you like to drink your coffee as hot as possible. And as we brew it, hot as possible is about 160 degrees Fahrenheit. You pour your cup of coffee, and the telephone rings, and it's your boss, and he wants to see you for 20 minutes. You want to keep your coffee hot, so you have to make a decision. Should you put the cream in right then and return in 20 minutes, or should you leave the coffee alone, come back in 20 minutes, and then put the cream in? In which scenario will you produce hotter coffee after 20 minutes? Now, the coffee we're going to be using is 10 ounces of coffee right after you brew it, which is about 160 degrees, and we're going to, at some point, add a half an ounce of cream, which is at 50 degrees. Now, when we do this, what we're going to do is we're going to record at the temperature when we first brew it, in the cream first scenario. After 30 seconds, we're going to add cream and stir it, and we're going to take a temperature, and then we're going to take another temperature after 20 minutes of letting it sit. So this is the cream first scenario. In the cream last scenario, we're going to leave the room, just let the coffee sit there after we've poured it, but we will take its temperature initially. We come back after 19 minutes and 30 seconds, we add the cream, we stir it, we take a final reading at 20 minutes. And we're going to find the cooling rate after cream and the cooling rate before cream. Now, this is our scenario, just so you can visually understand it. We have a cup of coffee, just comes out of the pot, stick in the thermometer, get a reading. As soon as it settles down, we stir it. We take cream, we pour it, stir it. About 30 seconds has passed, we take another reading, we walk away, we come back in 19 minutes, 30 seconds later, and take our final reading. In the second scenario, you get the coffee out of the pot. It's going to be somewhere around 160 degrees. But we're going to take our temperature. We're going to go walk and go and do whatever we have to do with our boss. It's going to sit there and cool. We're going to come back after 19 minutes and 30 seconds. We're going to take the reading then. At that point, we'll add the creamer. We'll stir it. Let it settle down a minute or a few seconds. And finally take our final reading at 20 minutes. And this is the result of doing that. We're going to put the data on the board now. Stop. This is how the results turned out. On the cream first scenario, when we took the coffee out and measured it immediately, we had 161 degrees Fahrenheit. We waited for 30 seconds, and we added cream, we stirred it, and we measured, and we got 149.7 degrees Fahrenheit. And when we came back after 20 minutes and measured, we got exactly 120 degrees Fahrenheit. So our final temperature, 161, minus, initial temperature 161, final temperature 120. Divide that by 20, and we come up with 2.05 degrees Fahrenheit per minute. When we did the cream last, when the coffee came out of the pot, it was at 159.5. We came back after 19 minutes and 30 seconds, it was reading 113.3. We added the cream, stirred, and took another reading, and it was at 110. So the overall differential here was 159.5 minus 110 divided by 20. That's 49.5, and it comes out to 2.47 degrees. What that shows us is the cooling rate is faster when we added the cream last. So if we wanted the hottest possible coffee, we would add the cream first. Now, one other thing we did was I wanted to look at the cooling rate after we creamed it. In this instance, it was the 149.7 divided minus 120, and we came up with 1.52 degrees. So degrees Fahrenheit per minute after you added the cream. In this scenario, we look at the times before we added the cream. And if we work it out, it comes out to 1.85 degrees Fahrenheit per minute. Again, it's cooling faster before you added the cream, which is in concert with our results, that hotter coffee will result from slower cooling, and slower cooling occurs because when you add the cream first, because you cut down the temperature differential early. And this is our conclusions. Our conclusions is cream last has a faster cooling rate. A hotter coffee, though, is when you add the cream first. And as we talked earlier, the cooling rate before creaming is faster than after creaming. Slower the cooling rate, the hotter the coffee, so add cream first. And the cooling rates are faster when the delta T is greater. That concludes today's lab on heat dissipation.